Good morning, I am Massimiliano Pirani and I am presenting towards a formal model of computation of RMAS. I present the context and the motivation of this work. There is a steady trend towards the introduction of multi-agent systems in industrial applications, in particular within the dominating cyber-physical system vision. The RMAS, the Relational Model Multi-Agent System, is an architecture and at the same time a framework that intends to speed up this transition. Though promising, RMAS still needs a handy but rigorous formalism, able to capture easily and conveniently the semantics of its model of computation. The model of computation should bridge also the disciplines of control and system engineering and computer science, while concerning artificial intelligence. This work should constitute the ground for industry-ready technological instances of the RMAS architecture. We start with some background. The RMAS architecture was introduced for a factual realization of networked and distributed automation with event-driven and database-centric paradigms towards advanced holonic multi-agent systems based on the best available technologies. RMAS has been challenged against the expectation of autonomic computing and self-start or self-X, which are essential for the introduction of artificial intelligence in the actual industrial realm. RMAS was proposed as an overlay for the IEC 61499 in order to facilitate the introduction of AI into the distributed computing provisions of the standard. We recall some fundamentals of RMAS. The event-driven information processing is made through an active database management system. An RMAS unit is made of an active database management system plus some libraries of procedural code in a host language invoked by means of a database triggers. An RMAS unit starts as a genotype containing only minimum provisions to further grow by means of an umbilical cord. You see on the left the genotype, which has got only one database table, and the trigger associated to that, which is able to trigger some relational processing on the message received. This allows inflating through SQL messages a full-fledged unit and endowing it with many features and many provisions, comprising an output stage and host language processing and materialized oracles that we will see in the host language indeed allows oracular computation. Querying an oracle can produce effects on the word of interest, being it physical or virtual, and including effectors of a system, physical, robotics, mechatronics, automation, or sensors, or even non-algorithmic computations like neuromorphic or quantum computing. So, in the figure we propose this vision where there is the algorithmic part, which is handled by relations and query, and then goes to the oracular part that produce results in the domain of the algorithmic part. In this work we have posed new definitions. The first one is concerning the concept of the actors in the actor model, and it is obtained also through distributed database. An RMAS unit can be given by means of the actor model. Actors are concurrent units communicating by asynchronous message passing. In response to an asynchronous message, an actor A1 with behavior beta 1 may perform one or more of the following actions. It can send a message to an acquaintance, an actor whose identity address is known to the actor A1, create a new actor A2 with a given behavior beta 2, or become ready to receive a new message carrying new behavior beta 2. Other new definitions here provided concerns with the 3 levels of RMAS. This is a new definition. The level 0 contains the bare elements that make up an actor. This is a subset of relations and triggers of a database management system on a device. Level 1 is the most common and basic RMAS unit presented in other literature. It features the full-fledged input and output stage of a device. And the level 2 is an RMAS unit over a distributed DBMS, such that the query language and the schemas are that of a distributed database across a set of devices. To go forward with RMAS and its formalization, we need a step further from relational model to lazy relational model. The lazy relational model is an extension of the relational model where there are no metadata describing the schema and the database language. All is a relation. LRM realizes the always open knowledge on top and at the bottom that characterizes current promising architecture in cyber-physical system of systems that follow a recursively open holonic approach for multi-agent system. In the lazy relational model, the definition of a type is not immediately grounded. This is called a lazy approach. It can be deferred until the instantiation of related extensional parts that define it, which possibly depend recursively from other relations. Moreover, lazy relational model needs a merge of the data definition language and the data manipulation language, which are typical of database management system definition, into an recursive relational language. This required first a new definition of relation, for which no meta references are made between the head and the body of the relation. Moreover, we define a set of operators that will be useful to express in shorthand notation the semantics of computation occurring along the RMAS. Note that, in general, data manipulation languages supports the following operation: insertion, deletion, update, and retrieval of data. The results of each operation is a relation here. So we define the U operator that generalizes the update, the I that denotes the inquiry of a database or information retrieval, the C that stands for the creation of a relation, the Q, which is collecting any of non-trivial composition of U, I, and C, and it is a relational operation in general. On the other side, we have the O, the oracular part. So O is an operator that takes into account any oracular, not strictly relational operation, invoking the host language. And then finally the T is a trigger with the following notation, made of 3 elements: an event, a condition, and an action. This formalization allows the representation of RMAS as an automata. This representation is fundamental and necessary towards the autonomous rewriting or reprogramming of autonomic computing through reactive synthesis. Our formalization goes in search of expression of omega languages for automata that would admit a state space representation for RMAS. We provided an example in the paper, a short example, but the concept is that this example shows also a never-stopping sequence that makes RMAS a reactive system and so an omega automation. Concluding with this work, a first step towards a formal model of computation for RMAS has been introduced. It has required the integration of the actual model with a new extension of the relational model, the lazy relational model, along with the suitable operators that allowed the expression of the status of the computation, its transitions and its semantics. Still, no full-fledged industrial implementation of the concept of RLRM has still happened. It requires more effort. A factual implementation of RMAS is at reach, but a specific implementation will depend on the application of a context, and it is open to the involvement of engineers and practitioners. The openness of the RMAS and its generality is to be seen as a feature of the RMAS architecture and not a limit. Thank you for attending.